You transfer money between two banks. One database deducts the money successfully. The other database, on a completely different server, fails to add it. Now the money has vanished from existence. How do real systems prevent this? Today, we are looking at the invisible safety nets that keep our entire digital economy from completely breaking down. We're going to explore exactly how large-scale systems manage to orchestrate complex actions across completely disconnected servers. They literally have to do this to make absolutely sure that your data, and more importantly, your money, is never just lost in the void. It's a massive engineering challenge, and the solutions are honestly pretty fascinating.
So you might be wondering, why is this scenario so incredibly hard to manage in the first place? Well, when you're building software, getting just a single computer to do something reliably is already tough enough. But when a single business operation has to succeed across multiple independent servers at the exact same time, the stakes go absolutely through the roof. Imagine you're buying a product online. You hit checkout. Your payment is processed by a server sitting in a data center somewhere in Virginia. Meanwhile, the inventory system, the one that actually reserves your physical item, is sitting on a completely independent server all the way over in Oregon. There is no shared memory between them. There's no single central brain controlling both of those servers at the hardware level. They are connected only by miles of unpredictable fiber optic cable. Each server can succeed, it can crash, or it can lose its network connection completely independently of the other one. If the payment server in Virginia thinks the transaction succeeded, but the inventory server in Oregon crashed a single millisecond before reserving your item, you just paid for something you're never going to get. And obviously, for any real-world business, that is a massive problem. To fix this, we have to talk about a core concept in databases. A database transaction is basically just a sequence of steps treated as a single unit of work. And for a normal, single database, it easily guarantees something we call atomicity. Atomicity is a strict guarantee where all operations succeed together or they all fail together. There is absolutely no halfway. If you move money between two accounts inside the exact same database, that database system controls everything internally. It manages the memory, it manages the hard drive, it sees the whole board. It can easily write the changes, check for any errors, and if anything goes wrong, it just scraps the whole attempt immediately. It's completely safe. But as we just discussed, real-world operations don't happen inside just one comfortable database anymore. They're spread out. Think of a normal, single-server transaction like one person signing a form. They either sign the piece of paper or they don't. It's right there in front of them. It's simple, it's immediate, and it is entirely under their control. But a distributed transaction, that is like needing signatures from people in 3 different countries at the exact same moment. None of them can see what the others are doing, none of them can talk to each other directly to coordinate, and at any moment, the phone line to any one of those countries might just go dead. How do you guarantee all 3 sign or nobody signs when they are entirely blind to one another? That is the engineering nightmare we have to solve.
So, let's dive into the first major solution engineers developed to solve this puzzle. It's a classic protocol called two-phase commit, often just referred to as 2PC. To make this work, two-phase commit introduces a totally new role called the coordinator. The coordinator is a central component that's specifically responsible for orchestrating the entire transaction across all the other involved servers, which we call the participants. Since the participants can't see each other, the coordinator acts as the central conductor, and it does this in 2 very distinct phases. Let's break down phase 1, the prepare phase. First, the coordinator sends a message out to every single participant server asking, "Can you guarantee you can commit this change?" Now, the participants don't just say yes blindly. They actually do all the heavy lifting required to be absolutely certain they can finalize the action. They write the upcoming changes to their own local disk logs, and they lock the required data so no other process can mess with it. This locking part is huge, but importantly, they do not make the changes permanent yet. They are just holding everything in a ready, frozen state. Finally, each participant replies back to the coordinator with a clear, "Yes, I'm ready," or a "No, I cannot do this." To really visualize what's happening here, think of phase 1 like a private wedding confirmation. Imagine a wedding officiant pulling both partners aside into a private room before the actual ceremony even begins. The officiant asks each person individually, "Are you absolutely certain you're ready to say yes?" Each person searches their feelings, confirms they are ready, and tells the officiant yes. Notice that nobody has committed publicly yet. Nothing is legally binding. If someone wanted to run away, they theoretically still could without a massive public mess. But the groundwork is completely laid out, and everyone has confirmed to the central authority that they are fully prepared to go through with it. And that perfectly sets the stage for the next crucial step, the actual execution. Once that private confirmation is secured from every single party involved, we move into phase 2, the commit phase.
This is where the actual action takes place, but it only happens under very strict conditions. The coordinator's sitting there, waiting patiently to hear back from every single participant it sent a prepare message to. It's an absolute all-or-nothing decision. If the coordinator hears a clear yes from every single participant, it blasts out a final instruction to everyone: commit. The participants then permanently write their changes to their databases and release all those data locks they were holding. Boom, done. But if even one single participant replies with a no, maybe the inventory server was completely out of stock, or maybe a server just timed out due to a bad network cable and didn't respond at all, the coordinator immediately shifts gears. It tells everyone to roll back. Every participant dumps their prepared changes, releases the data locks, and it is exactly as if the transaction never happened at all. This is how you achieve true atomicity across multiple independent servers.
Going back to our analogy for just a second, Phase 2 is the public I do at the altar. This is the exact moment both partners say I do out loud in front of everyone at the exact same moment. But you have to remember, this public commitment only happens because the efficient already privately confirmed both were certain beforehand. If either partner had hesitated or said no back in that private room, the ceremony would have been canceled entirely. The guests would have been sent home. They would never have reached this public moment at the altar. It requires total consensus.
But here is the massive plot twist. Two-phase commit sounds foolproof, right? It perfectly guarantees that all servers commit or none do. But it has a terrifying Achilles heel. What happens if the coordinator crashes at the absolute worst possible millisecond? Imagine Phase 1 finishes perfectly. Every single participant has locked their data, written their logs, and told the coordinator, yes, I am completely ready. The coordinator receives all those yes messages, prepares to send out the final commit instruction, and then its physical hardware fails. The power supply blows out, it crashes completely, and goes offline right before sending that final command.
This triggers what engineers ominously call the blocking problem, and it is a complete nightmare for system availability. All the participant servers are now stuck. They are completely frozen, holding data locks, sitting in a prepared but totally undecided state. If you remember, holding a data lock means no other system can read or write to that specific piece of data. They're completely unable to safely commit because they don't know if another server might have failed at the last second, meaning the coordinator was actually going to tell them to roll back. But they are also completely unable to safely roll back because they explicitly told the coordinator they were ready, and the coordinator might have been just about to tell everyone to commit. They are trapped in limbo, and while they wait for a coordinator that isn't there, your entire database grinds to a halt.
To drive this horrifying scenario home, imagine this happening at our wedding. Both partners have already privately confirmed, I'm ready to the efficient. They're standing at the altar in front of their families, and right before the efficient can announce anything publicly to finalize the marriage, the efficient suddenly collapses on the floor, completely unconscious. Both partners are now just frozen at the altar. They're unsure whether to walk away in tears and cancel the wedding or just stand there awkwardly holding hands. They are paralyzed because neither of them knows what the efficient was about to say. That is the blocking problem. And when it happens to a massive database, it can literally take down an entire company's infrastructure. Because of this massive risk, the industry realized we needed a completely different approach.
Because of this fatal blocking problem and just the general slowness of locking data across slow network connections, modern tech had to invent a new way, and that is the Saga pattern. This is the modern alternative that powers most of the highly distributed systems you interact with today, especially those built on microservices architectures. It completely abandons the idea of a central coordinator holding everyone in suspense with data locks. A Saga pattern is an architecture that breaks a massive distributed operation into a sequence of smaller, localized transactions. Instead of trying to magically force 5 different servers to commit at the exact same millisecond, a Saga lets each server do its work locally and finish immediately. But here is the brilliant key to the whole thing. Every single local transaction must have a corresponding compensating action. A compensating action is just a pre-programmed way to cleanly undo whatever was just done, just in case a later step down the line ends up failing.
Let's use a travel booking analogy to see how this works in practice. It makes it super clear. Imagine you're booking an entire vacation online. Step 1, the system books your flight on the airline's server. That local transaction finishes immediately and successfully. Step 2, it moves on and books your hotel on the hotel's server. That also finishes immediately. But then step 3, it tries to book your rental car, and the car company's server is down. The car booking fails entirely. In an old two-phase commit system, your whole vacation would have been held hostage in a locked state until the end. But with a Saga, the system simply catches the error and triggers those compensating actions in reverse. It sends a specific message to cancel the hotel booking, then it sends a separate message to cancel the flight booking. You don't need a magical instant rollback. You just systematically cancel each booking individually using its own specific cancellation policy. It is so much safer and doesn't block other users.
If this is the kind of content you want more of, subscribing takes 1 second and it genuinely helps the channel grow.
Now, let's take a step back and compare these two titans of system design directly, because they really serve completely different purposes. When we look at consistency, two-phase commit offers strong, true atomicity. Everything is perfectly synchronized. Saga, on the other hand, offers what we call eventual consistency. This means there's a brief window of time where your flight is technically booked but your car isn't, right before the cancellation messages manage to catch up. Looking at failure handling, two-phase commit has that terrifying blocking problem if the coordinator crashes. Saga handles failures beautifully by just firing off those compensating actions, so no system ever gets blocked waiting for a central authority. Performance-wise, two-phase commit is painfully slow because you're holding database locks open across unpredictable internet networks. Sagas are significantly faster because they only rely on quick local database transactions. And finally, the use case. You'll still see two-phase commit deep inside traditional, tightly integrated distributed databases. But for modern microservices and long-running business workflows, Saga is absolutely the undisputed king.
So, with all this incredible engineering at your fingertips, how do you actually choose your strategy? You might think that because these solutions exist, you should just use them everywhere to be perfectly safe. But the reality of system architecture is a bit more grounded. The most practical takeaway you can get from this entire topic is this simple rule of thumb. Avoid distributed transactions unless genuinely necessary. Distributed transactions, whether you use two-phase commit or a Saga, add massive complexity to your code. They add serious performance overhead, and they create wildly difficult debugging scenarios. Trying to trace an error across 5 different independent servers is an absolute nightmare. If you can restructure your architecture so that a critical operation stays within a single database or a single service, do that instead. It is vastly simpler, it runs much faster, and you completely avoid these terrifying failure modes. You should really only reach for these complex patterns when a business operation absolutely must span independent systems that you simply have no way of combining.
And that brings us right back to where we started, the vanishing money. You transfer money between 2 banks. One database deducts the money successfully. The other database, on a completely different server, fails to add it. Now the money has vanished from existence. How do real systems prevent this? Well, they prevent it because those independent banking servers don't just hope for the best. They are running incredibly robust distributed systems behind the scenes. Often, they are using sophisticated Saga patterns that ensure if the money cannot be successfully added to the destination, a compensating action fires immediately to refund your original account. Your money doesn't vanish because the architecture is explicitly designed to assume failures will happen and strictly orchestrates the cleanup. So the next time you tap your phone to pay, ask yourself, what hidden complexities are quietly keeping your digital world from falling apart today?